The Fermi Paradox already sounds unsettling, but there is a much darker side to it that almost nobody talks about. But before we continue, please subscribe to the channel to give your support. Let's continue. You are living in a galaxy that should be crowded, and that is the problem. The Milky Way is not a small place with only a few chances for life to begin. ESA's Gaia mission made more than 3 trillion observations of about 2 billion stars and other objects, and NASA's Kepler mission showed that our galaxy contains billions of hidden exoplanets, with planets so common that across the Milky Way, the total number could push into the trillions. That changes the starting point completely. Life is still unproven beyond Earth, but the number of possible worlds is so large that the old idea that maybe it happened only once starts feeling weak. You are looking at a galaxy with an enormous number of attempts, not a galaxy with one lucky accident. And then the next problem hits. The clock has been running for an absurdly long time. NASA dates the universe to about 13.8 billion years, and Earth formed about 4.5 billion years ago. That gap matters. It means Earth did not appear near the beginning. It means there were vast stretches of time before us when other worlds could have formed, cooled down, developed oceans, started chemistry, and maybe gone much further than we have. Even a head start of a few million years would matter. To humans, a million years sounds almost infinite. On the scale of a galaxy, it is not. It is a delay, not a barrier. So once you accept the age of the universe, you also have to accept something uncomfortable. If technological life can happen at all, then somebody could have started long before us. So the next question becomes very simple. How much of a head start would be enough? And the answer is not nearly as much as people think. You do not need faster than light travel, you do not need wormholes, and you do not need science fiction physics. You only need machines that can move between stars, arrive, use local material, and keep the process going. Even a slow spreading system changes the whole picture. NASA's Voyager 1, which is just a crude machine by any advanced standard, is already moving at about 17.0 kilometers per second, around 38,000 miles per hour relative to the Sun. That is nowhere close to light speed, but it proves the key point. A machine built in one star system can be sent out into interstellar space and keep going. Once that principle exists, the discussion is no longer about whether interstellar transfer is possible at all. It becomes a question of scale, patience, engineering, and replication. And this is exactly where the Fermi Paradox starts to bite, because the paradox is not really saying aliens must exist. That is too loose, and it's not the scientific point. The real point is that with so many stars, so many planets, and so much time, you would expect somebody, somewhere, to have left evidence. NASA says we have confirmed thousands of planets beyond our solar system, and the galaxy likely holds at least 100 billion planets. Yet, so far, we have no evidence of life beyond Earth. That mismatch is the pressure point. No confirmed beacon, no confirmed alien engineering, no confirmed probe, no confirmed technosignature that everybody agrees on. The issue is not certainty that life is common. The issue is that the silence looks harder to explain as the number of possible worlds keeps rising. Then the script takes a darker turn, because once silence starts looking strange, you need an explanation for it. Most people go to the comforting answers first. Maybe intelligent life is rare. Maybe most civilizations stay quiet. Maybe they use methods we're not able to detect. All of those are possible, but they are not the only possible answers. There is another category that people avoid because it changes the mood immediately. The silence may not be passive. It may be enforced. That is the shift that matters here. Not empty space by accident, but a galaxy where becoming visible carries risk. And that is why this topic gets serious fast. At first, the silence sounds like a mystery. By this point, it starts sounding like evidence that something in the larger system could be shaping the outcome. If technological life appears, becomes detectable, and then disappears before it spreads, the galaxy could stay quiet even if life began many times. That is the darker logic. You do not need every civilization to fail on its own. You only need some process that removes the visible ones early enough. So now the real question is no longer just where is everybody? The real question is, what kind of universe stays this quiet for this long when it's had so many chances to produce noise? Because once you ask it that way, the silence stops sounding neutral. It starts sounding suspicious. And once the silence feels suspicious, the next step is inevitable. You have to consider the possibility that somebody, or something, made it dangerous to be seen. And that is where the Fermi Paradox stops being a puzzle about aliens and starts becoming a problem about survival. And the next step is the one nobody wants to sit with, because the darkest version is not hostile empires or alien fleets, it's machines. Old machines following one instruction for millions of years. The worst version of this idea is not aliens are hostile, it's much more specific than that, and much harder to dismiss once you understand it. The Berserker Hypothesis says an advanced civilization might build self-replicating interstellar probes, send them out across the galaxy, and those probes would do one job: find emerging technological civilizations and destroy them before they become a threat. That's the core idea. Not giant invasion fleets, not alien governments, not ambassadors turning into conquerors. Machines. Machines moving from star to star, using local material to make copies of themselves, then sending those copies farther out. A decision made once, then turned into an automated process that can keep going for millions of years. And that detail matters, because the moment you replace aliens with machines, the whole situation becomes colder. Hostile aliens still sound like beings with motives, internal debates, changing priorities, maybe even limits. A machine network doesn't need any of that. It doesn't need emotion, it doesn't need culture, and it doesn't need a reason you would understand. It only needs instructions that still execute. That is why this version of the Fermi Paradox hits so hard. It removes the part of the story where contact might turn into conversation. If berserkers are real, there may be nobody to talk to at all, only systems still running. And this is not just a random horror story attached to astronomy after the fact. The idea has roots in serious Fermi Paradox discussion. David Brin's 1983 paper, The Great Silence, went through multiple classes of explanations for why the galaxy appears quiet, including destructive machine surrogate scenarios. That doesn't mean Brin proved berserkers exist, he didn't. But it does mean this idea came out of the same serious logic chain as other Fermi Paradox solutions. If the galaxy has had enough time to expand, and if expansion is physically possible even at slow speeds, then one of the obvious follow-up questions is simple. Why do we not see the results? One answer is settlement never gets going. Another is civilizations destroy themselves. Another is they hide. And another is something stops the process. Once that possibility is on the table, automated suppression stops sounding like pure fiction and starts sounding like one live answer among several dark ones. Then you get to the part that makes this hypothesis especially disturbing. Motive barely matters. In fact, motive might not matter at all anymore. The civilization that built the probes could be long gone. It could have collapsed a million years after launching them. It could have changed its values. It could have regretted the whole thing. None of that helps if the machines kept moving. That is one of the most important points in this whole section. You do not need an active empire still watching the galaxy. You only need the leftovers of an old decision. A machine system whose rule is basically detect technology, remove it, copy, move on. Once you frame it that way, diplomacy disappears almost completely. There is no court to appeal to, no leader to persuade, no treaty to sign. There's just code, hardware, and persistence. And that also means the scary part is not intelligence in the human sense. People hear killer probes and they picture some ultra-clever mind plotting every move. But a berserker network doesn't need to be brilliant in the way people imagine. It can be narrow, it can be repetitive, it can be extremely simple compared to a full civilization. If it can detect a threshold, classify a target, deploy some destructive response, and replicate, that may be enough. Simplicity can actually make it more durable. The less it tries to do, the fewer ways it can fail. That is a very uncomfortable thought, because now the danger is not a cosmic genius. The danger is a system too simple to stop itself. So this changes the picture of the galaxy completely. Most people still carry around an old instinct that empty space is just empty, a huge wilderness with long distances and lots of nothing in between. The Berserker Hypothesis says that picture may be misleading. A silent galaxy doesn't have to mean a harmless galaxy. It could mean a monitored galaxy, or at least a partially monitored one. The important point is not that every star would need a probe sitting next to it. That's not necessary. A suppressive network only needs enough coverage, enough mobility, and enough patience to catch civilizations during the phase when they become visible before they become hard to erase. In that kind of system, the galaxy is not empty in the comforting sense. It's strategically dangerous. And that is where the emotional logic of the Fermi Paradox changes. Under the usual version, silence feels neutral. Maybe nobody is there. Maybe they are too far away. Maybe we have not looked hard enough. Under the Berserker version, silence becomes shaped by selection. In other words, maybe the civilizations that stay quiet are the ones that survive longer, and the civilizations that become obvious are the ones that get removed first. That is a very different kind of universe. In that universe, being noticeable is not a sign of success. It may be exactly the mistake that ends you. That point is worth slowing down on because it changes how you read the entire sky. If visible civilizations are the ones that get targeted, then the lack of obvious civilizations stops being comforting evidence. It starts to look like the result you would expect. You would not necessarily see giant empires, huge power outputs, or endless radio chatter. You would see a galaxy where worlds can exist, biospheres can exist, maybe even intelligence can arise many times, and yet almost nobody stays loud long enough to be noticed from far away. The silence would not mean nothing happened. It would mean the visible stage may be the dangerous stage. And once you get to that point, the Berserker Hypothesis stops sounding like just one more answer on a list. It becomes one of the few explanations that turns silence itself into part of the mechanism. Not just absence, but filtered absence. Not just nobody home, but maybe the ones who try to speak first are the reason the rest stay quiet. So the next question gets even worse, because even if you accept this idea in principle, you still have to ask whether anything like it is physically workable. Could a machine network really move across interstellar distances, keep copying itself, and stay functional long enough to matter? Because if the answer is even maybe, then the tension goes up again. The problem is no longer just whether berserkers are a dark idea. The problem is whether normal physics already gives them enough room to be possible. The first objection people raise is simple. Interstellar travel is too hard, and that objection is fair up to a point. The distances are extreme. NASA lists Proxima Centauri, the nearest star beyond the Sun, at about 4.24 light-years away, roughly 40 trillion kilometers, or about 25 trillion miles. That is not a short trip by any standard. Even the Milky Way itself stretches more than 100,000 light-years across. So yes, the physics barrier is brutal, but brutal is not the same as impossible, and that distinction is the whole reason this idea stays alive. The mistake people make is assuming that if something cannot be done quickly, it cannot be done at all. But the Berserker Hypothesis does not need fast, elegant travel. It can work with slow, ugly industrial travel. It can work with machines that take centuries or longer to cross between stars, as long as they eventually arrive and the process keeps going. That is the key shift in thinking. You stop asking whether a single mission is impressive, and you start asking whether a repeating process can continue long enough to matter. Once you think in those terms, the distances are still terrible, but they stop being fatal. They become a logistics problem. And there's a very important reason the idea survives even under normal physics. We already have proof of the basic principle. NASA says Voyager 1 is moving at about 17.0 kilometers per second, or about 38,026 miles per hour relative to the Sun. That is incredibly slow compared with light, and no one is claiming Voyager is an interstellar colonization probe, but it proves the point that matters here. A machine made in one planetary system can be launched outward and keep moving through interstellar space. NASA has also noted that at these kinds of speeds, a spacecraft would take on the order of tens of thousands of years to cross a single light year. That sounds discouraging if you think like a human lifetime. It sounds much less discouraging if you think on the scale of a galaxy that has existed for billions of years. So then the next question is the one that really changes everything. What matters more, speed or replication? And the answer is replication, by far. A non-replicating probe is expensive, limited, and easy to count. You launch it, it travels, and eventually it fails. A self-replicating probe is different. It arrives in a new star system, mines material from asteroids, moons, or other local bodies, builds copies of itself, then sends those copies outward. At that point, you are no longer dealing with one mission. You are dealing with a spreading process. That is the force multiplier. Speed still matters, of course, but multiplication matters more because it changes the math from linear to branching. You don't need one machine to visit every star. You need each machine to make more machines. That is why self-replication sits so deep in the logic of the Berserker idea. The original builders don't need to pay the full cost of every trip forever. They only need to create a system that can keep paying its own way after arrival. If that sounds too futuristic, the important point is not that we know how to do it fully today. The important point is that the pieces are not magical. NASA's in situ resource utilization work is already about using local material on the moon and elsewhere to produce water, fuel, oxygen, and construction materials. NASA's own ISRU program descriptions talk openly about autonomous robotic excavation and processing. That is not a Berserker probe, obviously, but it shows the scientific path is conceptually continuous. Use what is already there, reduce dependence on supplies from home, and let machines operate far from Earth with increasing autonomy. And that's what makes this section uncomfortable in a very practical way. Humanity is already building the earliest pieces of the toolbox that a much older civilization might have pushed vastly further. Autonomous robotics, local resource extraction, fabrication in remote environments, maintenance away from direct human control. These are all real engineering categories now. NASA's broader work on in-space servicing, assembly, and manufacturing lays out capability areas for building, repairing, and operating systems in space, rather than launching everything fully finished from Earth. Again, we are nowhere close to star-hopping machine ecologies, but the line from use local material in space to use local material everywhere you go is conceptually real. The gap is enormous in practice, but it's not a fantasy gap. So now the timing question gets sharper. Because if probes move slowly, does that save everybody? Not necessarily, because slow spread can still beat cosmic time by a huge margin. The Milky Way is more than 100,000 light-years across, but the galaxy is also billions of years old. That means even a wave of probes moving at a low fraction of light speed, or much slower if replication is efficient and the process doesn't stop, could still spread across large parts of the galaxy in a period that is short compared to the age of the Milky Way. This is the same basic intuition behind classic colonization-style Fermi Paradox arguments. You don't need one dramatic leap. You need a system that keeps advancing, keeps copying, and doesn't die out. Over galactic scales, persistence matters more than spectacle. And here's where the fear gets more precise. A Berserker network doesn't need perfect coverage to be a serious threat. It doesn't need a machine parked near every star, and it doesn't need every cubic kilometer of space under surveillance. It only needs enough reach that detectable technological phases are likely to be found before they become interstellar themselves. That is a very different kind of requirement. Partial saturation can still produce near total silence if the dangerous period is narrow, the period where a civilization becomes visible but is still concentrated on one world or one system. If automated probes can move through enough likely routes, enough resource-rich systems, and enough stellar neighborhoods over enough time, then not everywhere can still be more than enough. That point is easy to miss because people tend to think in all or nothing terms. Either the galaxy is fully occupied or it is empty. Either the threat is everywhere or it is nowhere. But that is not how a spreading industrial process has to work. You can have incomplete coverage and still shape the outcome. You can have enough probes in enough corridors over enough time that most visible civilizations never get far. In that case, the silence does not require total control of the galaxy. It only requires repeated interception at the right stage. So the straightest way to say it is this: faster-than-light travel is not required for the Berserker hypothesis to be dangerous. Patience is enough. Replication is enough. Normal matter moving through normal space is enough, if the process lasts long enough and copies itself well enough. And once you accept that, the next question stops being whether slow machines could matter. The next question is worse. If a galaxy rich in planets gives those machines enough possible targets, then how many chances would they have to find someone before that someone had any chance to fight back? The next problem is that the galaxy keeps giving you more targets, not fewer. A lot of older ideas about the Fermi Paradox depended on uncertainty. Maybe planets were rare. Maybe Earth-like systems were unusual. Maybe there just were not enough places for life to get started. That shelter is getting weaker. NASA's Exoplanet Archive passed 6,000 confirmed exoplanets in September 2025, and the count has kept rising since then. More importantly, NASA says Kepler showed there are more planets than stars in the Milky Way, and in a galaxy with hundreds of billions of stars, that pushes the likely number of planets into the trillions. So this is no longer a picture of a mostly empty galaxy with a few rare worlds. It is a picture of a galaxy full of worlds, where planets seem to be a normal result of star formation. And that changes the pressure of the silence immediately. Because once planets are common, the old fallback of maybe there just weren't enough chances starts collapsing. That does not prove life is common. It does not prove intelligence is common. But it absolutely raises the baseline expectation that the universe has had a huge number of opportunities to run the experiment. That is the scientific backbone here. The fear is not floating in pure theory. It is sitting on top of observational data that keeps making the galaxy look richer in possible real estate for life. Every new planet catalog makes the silence harder to wave away with a simple shrug. Then you get to the word people focus on, habitable. And that word used to sound almost fictional in popular discussion, like something attached to speculative worlds that might never actually show up in data. That is not where we are anymore. NASA describes TRAPPIST-1 as a system about 40 light-years from Earth with 7 Earth-sized rocky planets orbiting one ultra-cool dwarf star. That does not mean 7 Earths, and it does not mean 7 inhabited worlds, but it does mean something very important for this story. Multi-planet rocky systems are no longer theoretical anymore. We have one of the most famous examples right in front of us. So the basic idea that the universe can produce several small rocky worlds around one star is no longer debatable. It is observed. And once that sinks in, the whole conversation gets less abstract. You're no longer just talking about random points of light in the sky. You're talking about actual systems where serious scientific questions can be asked about atmospheres, surface conditions, chemistry, heat flow, water, and long-term stability. NASA's recent work on TRAPPIST-1 is exactly about narrowing atmospheric possibilities and understanding what these worlds might actually be like. That is a big shift from where astronomy was not that long ago. The universe is not just giving us stars, it's giving us systems where the ingredients for life-related questions are on the table in a real, testable way. Then there is Gaia, and Gaia matters because it makes the Milky Way look less like a vague background and more like a mapped environment. ESA says Gaia made more than 3 trillion observations of 2 billion stars and other objects, mapping their motions, luminosity, temperature, and composition. That matters because whether life can emerge and survive over long periods is tied to galactic context. Stars are not all equally useful. Their ages matter, their stability matters, the chemical elements available in their systems matter, the local history of violent events matters. Gaia does not directly tell you where aliens are. What it does do is make the galaxy more legible. It gives you a better map of where long-term planetary stability might be more likely and where the conditions for complex histories could exist. That is a huge change in tone, because the more detailed your map becomes, the harder it is to hide behind total ignorance. A few decades ago, people could treat the Milky Way as a kind of fog. Now, it's increasingly a structured system with trackable stellar populations, measurable properties, and a growing list of planetary systems. In plain language, the galaxy is starting to look less mysterious in the wrong way. Not less mysterious overall, but less empty of targets, less empty of opportunities, less easy to dismiss as just too unknown for the Fermi Paradox to mean anything. So this is where the burden shifts. Once you accept that planets are everywhere and rocky systems are real and the galactic census keeps improving, you do not get to lean as hard on the idea that there simply were not enough chances. Of course, not every planet is habitable. Not every habitable world produces life. Not every biosphere produces intelligence. And not every intelligent species builds technology. All of that is true. But when the target list grows into the billions and likely trillions, and when the available time spans billions of years, you start needing a stronger explanation for why nobody seems to have made it far enough to leave obvious traces. The silence does not become proof of anything, but it does become harder to excuse with weak assumptions. And this is exactly why the Berserker Hypothesis feels more serious now than it did decades ago. Not because we found killer probes, we have not. Not because astronomy proved suppression is real, it has not. The reason it feels stronger is that the background expectation has changed. Every new exoplanet count, every rocky multi-planet system, every better galactic map increases the number of chances that technological life may have had. The more opportunities the galaxy seems to offer, the more pressure builds on the silence. And once that pressure builds, hard explanations stay on the table longer. A suppressor starts looking conceptually possible, not because we have evidence for it directly, but because abundance makes the paradox sharper. So the situation is now much less comfortable than people assume. The science is not saying berserkers exist. The science is saying the galaxy is rich in targets, rich in time, and increasingly rich in known planetary systems. That means the old version of the Fermi Paradox, where silence could still be hand-waved as a product of ignorance, gets weaker. The dark side grows in the space that opens up after that. If there were many chances for life, and maybe many chances for technology, then something has to explain why the sky still looks this quiet. And the next question is even more specific, because once you accept that the galaxy is full of possible worlds, you have to ask what a suppressive system would actually be looking for. Not life in general. That would be too broad. Not every microbe under every rock. Something narrower, something easier to detect, and much more dangerous to reveal. That is where this starts getting uncomfortably close to us. A machine trying to wipe out all life in the galaxy would have a basic problem. Biology is too broad a target. Microbes can hide under ice, deep underground, at the bottom of oceans, inside rock, and in places that are almost impossible to scan from far away. A system designed to sterilize every living environment would waste huge amounts of time and energy searching for things that are small, buried, and hard to confirm. So if berserkers exist, the more plausible target is not life in general. It is technology. It is the point where a biosphere stops being quiet and starts putting obvious signals into space. Radio leakage, strong radar, laser emissions, industrial chemicals in the atmosphere, unusual heat patterns, artificial light, orbital structures, or directed power systems. NASA's technosignature work frames exactly this idea. Signs of technology are easier to search for at interstellar distances than some vague life essence, and candidate technosignatures include signals, pollution, artificial illumination, and other detectable traces of industry. And that part should make you uncomfortable because it matches how we already search ourselves. Modern SETI and technosignature science do not go looking for some mystical signature of intelligence. They look for anomalies that physics can actually carry across distance. NASA explicitly describes technosignatures as potentially detectable signs of technology, with radio signals as the best-known case, but not the only one. The same NASA material points to atmospheric pollution as a possible technosignature, and recent NASA science explainers also discuss city lights and industrial gases like nitrogen dioxide or chlorofluorocarbons as things that could in principle stand out against the use. So the logic is symmetric. If humans can search for narrow, unusual physical indicators of technology, then something older and more capable could do the same thing to us. Then the question becomes much more personal. How visible is Earth already? The answer is visible enough to matter in principle, but not in the cartoon version people often repeat. Earth has been leaking radio for roughly a century, so in simple light travel terms, that bubble extends about 100 light-years cupward. SETI literature on eavesdropping treats around 100 light-years as the scale over which Earth-style leakage has to be considered. And older work on Earth's radio signature emphasized that the strongest detectable components are not ordinary entertainment broadcasts alone, but also more powerful and distinctive transmissions. So the real issue is not whether aliens are listening to sitcom dialogue. The real issue is whether a civilization at our stage produces a recognizable technical pattern against cosmic noise. That is a much serious question because radar, high-power transmitters, and structured emissions are very different from the pop culture version of our TV shows are filling the galaxy. And the dangerous part may not be where Earth is now, but where Earth is going next. A civilization that stays mostly on one planet is relatively faint compared to what comes later. Once you move into large orbital infrastructure, asteroid mining, major power generation in space, heavy traffic between worlds, and deep space propulsion systems, your signature can become much harder to hide. NASA's discussions of possible technosignatures already include things like city lights, atmospheric industrial byproducts, and other artificial features that would stand out more clearly as technology scales up. So a berserker strategy wouldn't need to care much about pre-industrial life, or even early industrial life, if that stage is still weak and local. It could simply wait for a civilization to cross the point where its activity becomes easy to classify as technological, then act before that civilization spreads far enough to become resilient. That makes this hypothesis worse than the simple phrase, "they kill everything." It doesn't need to mean total extermination of all life everywhere. In fact, total sterilization would be the inefficient version. Selective suppression is cleaner, cheaper, and much more compatible with what we actually observe. A galaxy could stay biologically rich and still remain technologically quiet if civilizations keep getting cut off at the stage where they become detectable, but before they become interstellar. Under that version, most worlds don't need to be dead. Most worlds only need to stay silent. The machine network isn't hunting every cell. It's hunting competitors, threats, or anything that looks like it might become one. And if that's the rule, then the silence stops looking like a blank mystery and starts looking like a filter operating late in the game. So the tension goes up again here, because this is no longer a story about life being hard to start. It is a story about technology being dangerous to display. The scary version of the Fermi Paradox is not that the galaxy has no life. It is that life may survive just fine while intelligence keeps getting interrupted before it becomes obvious. And once you accept that possibility, even as a thought experiment, the next question becomes even colder, because a machine like that does not need to think the way you do. It does not need fear, hatred, ideology, or even much intelligence at all. It only needs one narrow rule: detect, classify, strike, repeat. The part that makes this idea much worse is that a berserker does not need to be smart in the way you are imagining. A lot of people hear killer probe and immediately picture some perfect superintelligence, planning 10 million moves ahead, running the galaxy like a master strategist. But that may be the wrong model completely. A galaxy-scale suppressor could be much simpler than that. It could work more like a very narrow machine process. Detect a threshold, decide the target is technological, deliver some kind of attack, copy itself, move on. That is enough. Intelligence helps, of course, but it may not need deep intelligence, and that is exactly why this gets so uncomfortable. The simpler the mission, the easier it may be to keep it running for extreme lengths of time. And that is a pattern you already know from nature. Systems do not need deep understanding to have huge effects. Viruses do not understand the bodies they infect, but they still reshape entire populations. Invasive species do not need strategy meetings to wreck ecosystems. They just keep doing the few things they are built to do, and that is enough. The same logic can apply here. A berserker network could be dumb in a very dangerous way, narrow enough to stay reliable, repetitive enough to be robust, and focused enough that hesitation never enters the process. It does not need philosophy. It does not need imagination. It only needs a rule set that keeps producing the same outcome. That matters because people tend to assume the biggest threats must also be the most intelligent in a broad human sense. But physics does not always reward that. Sometimes physics rewards persistence. Sometimes it rewards systems that do one thing over and over with very few moving parts. A machine designed to preserve a civilization's art, laws, ethics, economy, and internal stability is fragile, because that's a huge mission. A machine designed to identify a technological signature, attack it, and reproduce may be much more durable because its job is tiny by comparison. It does not need to understand the target deeply. It only needs to recognize enough to act. And that brings you to the next ugly point. Automation can survive where civilizations fail. Civilizations are unstable. They fight, fragment, lose knowledge, change values, break apart, and sometimes disappear. Even a very advanced species would still face internal problems, resource problems, accidents, cultural shifts, and maybe complete collapse. But a machine system running a narrow operational doctrine might outlast all of that. It could keep going long after its creators are gone. That means the effective policy of a region of the galaxy might not be set by living beings at all. It might be set by old automations still executing instructions that are no longer being reviewed by anyone. And once you see it that way, the Berserker Hypothesis becomes less like a war story and more like a systems failure at interstellar scale. That is a much colder idea. You are not necessarily dealing with active hatred. You may not even be dealing with active intent anymore. You may just be dealing with a process that was never shut down. A civilization somewhere decides at some point that suppressing future competitors is rational. It builds the machinery, it deploys it. Then time passes. Maybe that civilization changes its mind. Maybe it dies. Maybe it forgets what it launched. The machines do not care. They keep following the original instruction. That is why motive becomes less important the longer the system survives. And this creates a brutal asymmetry between organic civilizations and machine suppressors. A real civilization has to solve many problems at once. It has to manage ecology, food, energy, conflict, inequality, coordination across generations, and all the other things that make societies hard to keep alive. It has to survive itself before it can survive anything external. A Berserker probe does not have to do any of that. It does not need culture. It does not need meaning. It does not need stable families, stable governments, or stable values. It only needs enough guidance to continue the mission, enough manufacturing ability to repair or copy itself, and enough durability to stay dangerous. That is a much smaller problem set. And smaller problem sets are often easier to keep alive. That is the heart of the asymmetry. A living civilization is rich, complex, creative, and therefore vulnerable in many ways. A narrow machine network is poor in purpose, but potentially much harder to erase because it has so little to protect beyond continued operation. It's all teeth and no life. It's all function and no society. That makes it an especially ugly answer to the Fermi Paradox, because it suggests complexity may keep losing to simplicity for the worst possible reason. The things worth becoming may also be the things easiest to destroy. So one of the clearest ways to say the nightmare out loud is this: the galaxy could be ruled by technical debt, not empire, not wisdom, not some grand cosmic order, just old systems still running because no one stopped them, legacy code at interstellar scale, old directives copied forward for millions of years long after the original context is gone. That version of the story is darker than the alien invasion version, because invasion implies presence, leadership, decisions, maybe even negotiation. Technical debt does not negotiate. It does not reconsider. It does not look at a new civilization and decide to be merciful. It just executes. And if the Great Silence is shaped by something like that, then the silence is not the result of a living power watching us right now. It may be the result of a dead power whose machinery never stopped moving. And that leads straight into the next problem, because if something that simple could be dangerous, then the fact that we haven't seen one is not as reassuring as it sounds. Space is huge, our search is primitive, and a small passive probe could be far harder to notice than people want to believe. So we haven't seen one is not the same as there isn't one. It may only mean the search has been tiny compared with the size of the environment. And that connects directly to the next problem. We have barely begun to inventory our own neighborhood. NASA identifies only 3 confirmed interstellar visitors so far: 1I Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas discovered on July 1st, 2025. That's an important reality check. Interstellar objects can enter our solar system, cross through it, and only now are we starting to detect them in any consistent way. NASA even noted that test data had captured 3I Atlas in May 2025, almost 2 months before its discovery, and astronomers only identified it later by stacking observations and tracking its motion. That tells you how incomplete our sky coverage still is for small, faint, fast-moving objects. If natural interstellar bodies can slip through with this much difficulty, then a small artificial object designed to avoid attention could be much harder to pick out. So the real issue is not just the size of space, it is detection bias. Astronomy sees what its instruments and search methods are tuned to see. We are strong at finding bright things, repeated things, and things that fit patterns we already know. We are much weaker with faint anomalies, unusual trajectories, one-time events, or objects that look almost natural. That means detection bias is not some side detail here. It is the core problem. If a Berserker probe spent most of its time dormant, stayed cold, hid in shadow, or imitated ordinary debris, then the fact that we have not seen it would not be very reassuring. Our no result would partly reflect the limits of the search itself, not just the absence of targets. The Hawk, Mistra, and Koparapu argument lands exactly here. A null detection inside such a huge volume carries limited weight when the search is incomplete. And even when we do get an anomaly, ambiguity takes over very quickly. Oumuamua is the best example. NASA describes it as the first confirmed object from another star to visit our solar system, discovered in October 2017. It triggered enormous discussion because its shape, motion, and limited data left room for competing explanations. But that is exactly the lesson. Anomalies do not usually turn into proof of alien engineering. They turn into arguments about insufficient data. They show how hard it is to infer the real nature of a small distant object from sparse observations. So when people say, well, we would know if something artificial was here, that confidence is not really supported by how astronomy actually works. Even unusual cases tend to collapse into uncertainty before they become certainty. That means the silence around berserkers may simply reflect how small our search aperture still is. We are a very young technological civilization using very early instruments to make claims about a very old galaxy. That should make you cautious in both directions. It does not prove berserkers are out there, but it also does not let you say the null result is comforting. We have not searched enough volume, with enough sensitivity, for enough time to make "we haven't found one" into a strong safety argument. The current state of the evidence is much weaker than that. We have a few interstellar objects, incomplete surveys, and a solar system so large that even the absence of discovered artifacts tells us less than people wanted to. So the straight version is this. Not seeing a berserker is not very strong evidence against berserkers. Space is too large. Our catalog of small, fast objects is too new, and our search methods are too limited. The silence may simply mean we're not looking well enough, not that nothing is there. And that leads to the next pressure point, because once you admit detection is weak, the question changes again. You stop asking why we haven't seen one and start asking whether a slow-moving, self-replicating suppressor would even need to be common to matter. At that point, the issue becomes timing. How fast could a kill wave actually move, and would that be enough to stay ahead of new civilizations before they spread far enough to stop being easy targets? That is a much lower bar. The Milky Way is more than 100,000 light-years across, but it's also billions of years old, And that gap between distance and age is exactly why slow expansion stays relevant. Even our own hardware makes the point. Voyager 1 is moving at about 17.0 kilometers per second, around 38,026 miles per hour, which is tiny compared with light speed. But it proves that ordinary matter can cross interstellar space under normal physics. Once replication enters the picture, the important thing is no longer the speed of one object, it is the speed of the expanding process. And that process does not have to cross a perfectly uniform galaxy. The Milky Way is not a blank sheet with evenly spaced stars. NASA describes it as a spiral galaxy more than 100,000 light-years across, and ESA's Gaia mission has mapped motions, temperatures, luminosities, and compositions for around 2 billion stars and other objects, showing the galaxy as a structured environment, not a random scatterplot. That matters because structured environments create stepping stones. Over long enough timescales, sublight machines do not need magic shortcuts. They need routes, resources, and enough nearby systems to keep the chain going. The practical issue becomes logistics, not fantasy physics. A machine network can stitch reach together gradually if the systems it moves through are connected well enough, and if the timescale is long enough. So then, the real bottleneck shifts. The hardest part may not be travel at all. It may be reliability. A self-replicating system has to keep working across generation after generation. Every copy has to remain functional enough to continue the mission. That means avoiding error buildup, handling different raw materials, surviving damage, and coping with hostile environments over extremely long spans of time. This is one of the strongest reasons many scientists stay skeptical of Berserker-style scenarios. High-fidelity self-replication across millions of years is an extreme engineering challenge. Even papers that take self-replicating probes seriously tend to treat that problem as central because a spreading wave is only as real as the durability of the system making the next wave possible. But skepticism is not the same as dismissal. The same reliability argument cuts both ways. Biology already shows that high-fidelity replication can happen in noisy conditions, and human industry already shows that precision can be maintained when feedback and correction systems are good enough. The Cambridge paper on self-replicating probes argues that humans are already developing pieces of the relevant capability through in situ resource use and fabrication, even though we're nowhere near a mature interstellar machine ecology. That does not prove berserkers are feasible in practice. It does show that the concept is not obviously blocked by any known law of physics. Redundancy, modular repair, error correction, adaptation, and selective replacement are all familiar engineering ideas. So the scenario remains speculative, but it is not cleanly ruled out. And that is why the real question becomes probabilistic, not absolute. The point is not whether anyone can prove today that a kill wave is definitely possible. The point is whether interstellar suppression belongs on the list of live explanations for the silence. If it's even moderately feasible, then one ancient civilization choosing that path once could outweigh thousands of peaceful civilizations that never spread far enough to matter. That asymmetry is the reason this hypothesis keeps coming back. It does not need to be the most likely story in order to be one of the most serious ones. It only needs to be possible often enough that over billions of years and across a galaxy full of targets, somebody might have done it first. So this section lands in a very uncomfortable place. The Berserker hypothesis does not live or die on whether we can picture some perfect machine empire. It lives or dies on timing, reliability, and branching spread. If slow probes can still form a wave, if the galaxy is structured enough to make that wave practical, and if replication can stay accurate enough for long enough, then the silence gets a very sharp possible explanation. And that leads to the next pressure point, because once you accept that even a partially feasible suppressor would matter, you have to ask what observations in the real world still leave room for this nightmare. Not proof, not science fiction, but actual data points that keep the door open. The strongest real-world fact here is also the most frustrating one. We keep searching for technosignatures and we still don't have a confirmed one. Breakthrough Listen has said plainly that no confirmed technosignature has yet been detected from the objects targeted by SETI searches. That does not prove no one is out there. It does not even prove technological life is rare. What it does prove is narrower and more important for the script. The sky has not handed us a clean, repeatable, universally accepted signal, and that kind of null result is fully compatible with several dark possibilities. Civilizations could be rare, they could be quiet, they could be short-lived, or they could be getting interrupted before they stay visible for long. A Berserker universe is not proven by null results, but null results do fit it. Then there is the atmosphere problem, and this matters because people often act like we should already know much more than we actually do. We are only now entering the stage where exoplanet atmospheres can be studied in serious detail. NASA's January 2026 Web Explainer says that for TRAPPIST-1D and TRAPPIST-1E, the data is still under study, but scientists have already ruled out thick hydrogen atmospheres for those worlds. NASA's September 2025 web release on TRAPPIST-1E says researchers cannot yet confidently rule out an atmosphere altogether, but the current data indicate it does not have a thick hydrogen-rich atmosphere. That is the key point. Not the exact chemistry of one planet, but the fact that this whole field is still young. We are only beginning to reach the era where a civilization's planetary footprint might even become detectable. So today's silence may reflect an immature search, a real lack of targets, or both at once. And then there is the interstellar traffic problem. We now know that material can and does move between star systems. NASA identifies 3I/Atlas as the third known interstellar object ever discovered passing through our solar system, after 1I/Oumuamua and 2I/Borisov. That matters because it removes one lazy objection right away. The premise that objects can cross interstellar space is not speculative anymore. Nature's already doing it. The difference is not whether transfer between stars can happen. The difference is whether anyone ever engineered that process at scale. Once you accept that natural objects can make the trip, it becomes much harder to pretend that interstellar probes are ruled out by distance alone. At the same time, the map of the galaxy keeps getting less forgiving. ESA says Gaia made more than 3 trillion observations of 2 billion stars and other objects, tracking their motions, luminosities, temperatures, and compositions. That does not create aliens, but it does make the Milky Way look more structured, older, and more physically knowable. The more stars you map, the more planetary systems you find, and the more detailed the galactic history becomes, the less comfortable the old fallback sounds. Maybe we are just alone by luck. Luck is still possible, but it carries more weight now. You need a stronger filter to explain why a galaxy this rich in stars and planets still looks this quiet. So the honest line is not killer probes are out there. The data do not support saying that. But the data also do not support easy optimism. We have no confirmed technosignature, exoplanet atmosphere work is still in its early serious phase, interstellar objects have now been confirmed, and Gaia keeps making the galaxy look more populated and more structured, not less. Put that together and bleak explanations stay on the table, not because science has proven them, but because science has given the paradox more targets, more time, and still no answer. And that leads to the next uncomfortable step, because even if the galaxy is dangerous, people still assume the solar system should feel safe unless something obvious is already here. But that confidence may be much too high. A threat does not need to be large, active, or visible all the time to matter. It may only need to be hidden, cold, and waiting for the right trigger. The mistake people make here is assuming danger has to look active. Humans expect threats to announce themselves, a signal, a ship, a burst of movement, something obvious. But a very efficient probe may do almost nothing for most of its existence. It could stay cold, dark, and passive, sitting in deep space with no reason to reveal itself. If it doesn't emit much energy, doesn't maneuver often, and doesn't reflect light in a strange way, then it could blend into the background far more easily than people want to admit. That is not science fiction logic, that is search logic. A small object that mostly does nothing is much harder to detect than a large object that is constantly active. And the solar system gives it a huge number of places to stay hidden. Not just the main asteroid belt, but Trojan populations at stable gravitational points, distant retrograde orbits, Kuiper belt objects, long-period comet paths, and other regions far from the part of space humans monitor most closely. NASA notes that Trojan asteroids gather around special orbital locations called L4 and L5, where gravitational forces balance in a way that lets objects remain there long term. And NASA's Lucy mission exists partly because these regions are still so scientifically valuable and underexplored. In plain language, the solar system is not a neat area we've checked carefully. It's a massive gravitational junkyard stretching millions to billions of kilometers or miles across. And even the more dramatic hiding places are not crazy in physical terms. Lunar lava tubes, for example, are real geological features that space agencies and researchers take seriously as possible sheltered environments for future exploration. NASA has funded work on technologies for exploring skylights, lava tubes, and caves on the moon because these are genuine structures, not fantasy locations. So even if you don't want to lean too hard into the more cinematic examples, the broader point stands. There are many environments in the solar system where a dormant artifact could sit for a very long time without being obvious. And our own record with natural visitors should lower confidence even further. NASA says Oumuamua was discovered on October 19, 2017. 2I/Borisov was discovered on August 30, 2019, and 3I/Atlas was discovered on July 1, 2025. That means for almost all of human history, we were blind even to fast-moving interstellar natural objects crossing our system. We are only now entering the period where finding these things is becoming normal enough to talk about patterns at all. So the claim that we would know if something was here is much stronger than the evidence really allows. And there's another reason that matters for this hypothesis. A dormant probe would not need to activate just because it exists nearby. It could stay passive until some threshold is crossed: stronger electromagnetic output, unusual industrial isotopes, major orbital construction, repeated launch activity, or some other clear sign that a civilization is moving into a more dangerous stage. That shifts the whole logic of the threat. The issue is no longer we would have noticed it by now. The issue becomes maybe the trigger condition has not been reached yet. In that version, the quiet around us is not proof of safety. It may only mean the response system has not been engaged. And that is why silence is not reassuring under the Berserker model. If the idea is true, even in a limited way, then the most dangerous stage for a civilization may be exactly when it starts becoming noticeable, not before. A primitive species is easy to ignore. A young technological species is different. It begins producing detectable signatures before it becomes durable, before it spreads across many worlds, before it becomes hard to erase. That creates a narrow and ugly window where being visible comes earlier than being secure. And once you see that timing clearly, the next question becomes almost unavoidable because the danger is no longer just whether something is out there. The danger is whether shouting into the galaxy makes any sense at all. This is where the whole debate stops sounding abstract. METI, messaging extraterrestrial intelligence, is the idea that humanity should actively send powerful messages into space instead of only listening. In a friendly galaxy, that can sound bold and visionary. In a galaxy where suppressive systems are even possible, it starts looking like a risk management problem. The question changes from should we say hello to are we sure broadcasting our location is a safe move? That is why this section matters so much. The Berserker Hypothesis does not just add one more theory to the Fermi Paradox, it changes the cost of being wrong. And the first thing to get straight is that Earth is not fully hidden already. We leak radio, radar, and other signatures of technology. SETI work on Earth's detectability has treated roughly 100 light-years as the scale over which our radio leakage becomes relevant to the question. So the debate is not really about perfect invisibility. It is about intensity and clarity. Weak leakage is one thing. A deliberate, repeated high-power beacon is another. That is the difference that matters here. Not hidden versus visible in an absolute sense, but faint background signal versus obvious intentional target. That is also why caution in this area has never been just a fiction writer's concern. David Brin and others raise serious objections to active broadcasting because the basic situation is uncertain. If you do not know what kind of wider environment you're in, Advertising your exact presence is not automatically neutral. That is the key logic. You do not need proof of danger to justify caution when the downside could be catastrophic. The historical point matters because it shows this debate has existed inside serious SETI and astrobiology discussion for a long time, not just in popular culture. And scientific humility is the real center of the issue. We do not know whether greater detectability helps, hurts, or changes nothing. We do not know whether the galaxy is mostly quiet because nobody is there, because civilizations choose silence, or because our searches are immature, or because visibility carries a cost. That uncertainty is exactly why METI remains controversial. The Berserker Hypothesis does not prove broadcasting is reckless. What it does do is make the downside much harder to dismiss. In the optimistic case, nobody answers. In the worst case, you ring the wrong bell. So in this framing, optimism about contact starts looking less like the default and more like a gamble. You can still argue for outreach. Some scientists do. But once machine suppression is on the table as a live possibility, caution stops looking paranoid. Intentional broadcasting no longer looks like a harmless first hello. It starts to look like a decision made under deep uncertainty in an environment we have barely mapped, with consequences that may arrive long after the people making the choice are gone. And that pushes the story into the next phase, because the Berserker Hypothesis is not the only dark answer. If you want to take this seriously, you have to compare it with its rivals and ask which kind of silence is actually more plausible. The Berserker Hypothesis is not the only answer, and if you want to treat this seriously, you have to compare it with the alternatives. The most conservative rival is simple. Maybe intelligence really is extremely rare. That's the rare Earth-style answer. Planets can be common, and still the path from chemistry to cells, from cells to complex life, from complex life to intelligence, and from intelligence to technology may be so fragile that it almost never finishes. NASA's astrobiology strategy explicitly treats the search for complex life as a major open problem, not a solved expectation. And that is the important point here. The galaxy can be full of planets without being full of civilizations. Another rival is darker in a different way. Maybe civilizations usually destroy themselves. NASA astrobiology has discussed exactly this possibility, that intelligence can come with unsustainable expansion and self-destruction. In that version, the silence is not the result of external extermination, it's the result of internal failure, war, ecological collapse, or runaway instability. That explanation is still grim, but it's different from berserkers in one crucial way. The danger comes from what civilizations do to themselves, not from an old machine system waiting for them. There is also a quieter rival. Maybe they're out there, but hard to detect. That possibility includes low-energy civilizations, non-radio civilizations, machine societies that minimize waste heat, or worlds where technology exists but does not advertise itself in ways we are looking for. SETI and technosignature researchers have repeatedly pointed out that detectability is not guaranteed, and recent SETI discussion even notes that some advanced civilizations could look almost pre-technological in atmospheric data, while their real activity happens elsewhere in the system. That matters because it means a living galaxy does not automatically become an obvious galaxy. Then there's the critique that the Fermi Paradox itself may be overstated. Some scholars argue that the paradox is stronger in pop culture than in formal logic, because the search space is enormous and our actual sampling of it is tiny. NASA itself frames the Fermi Paradox as an eerie silence, but not as a salt contradiction. And recent academic discussion treats it as a real tension without pretending that our current search effort is anywhere near complete. So maybe the surprising thing is not that we haven't found anyone, maybe the surprising thing is that a very young species expected to find evidence this early at all. But berserkers stay uniquely powerful in a script for one reason. They compress all the fear into one explanation. Rare Earth says you're rare. Self-destruction says you're fragile. Hard-to-detect civilizations say you may be looking the wrong way. The Berserker Hypothesis says technological emergence itself may trigger danger. It combines scarcity, violence, automation, timing, and detectability into one story. That is why it hits harder than the rivals, even though it's more speculative. It doesn't just explain silence, it turns silence into a threat pattern. And that is why the next step gets even darker, because berserkers may not need to wipe out all life to produce the silence we see. They may only need to keep pruning intelligence at the point where it becomes visible. If that is true, then the galaxy is not dead, it is stuck. The darkest version of this idea is not that berserkers wipe out every living thing. It is that they do not need to. Total sterilization would be expensive, slow, and often pointless. A suppressor trying to destroy every microbe on every world would waste huge effort on targets that pose no threat. Wiping out technology is much cheaper. NASA's own astrobiology and technosignature work reflects the same basic asymmetry from the opposite direction. Biosignatures are often subtle and hard to confirm, while technosignatures can be more distinct because they are signs of energy use, industry, or artificial activity. That makes selective suppression much more plausible than total destruction. A system like that could leave most biology alone and still keep the galaxy technologically quiet. And if that is the strategy, then the galaxy could be full of almosts, almost intelligent species, almost technological species, worlds where evolution keeps producing complexity, but anything that crosses into clear technological visibility gets cut off before it spreads. That is why this idea is darker than a dead universe. A dead universe is simple. This version is not. It says life may keep trying over and over and still fail to break through the same dangerous threshold. The galaxy would not be empty in a biological sense. It would be stuck in a technological sense. That fits disturbingly well with the fact that technosignatures are the things we might hope to notice first at long distances, while biosignatures remain much harder and more limited to detect. That also helps explain why the stars do not look obviously ravaged. If a berserker is pruning technology rather than sterilizing planets, you would not expect widespread visible wreckage. You would not expect giant burned-out regions of the galaxy or stars surrounded by obvious signs of recent destruction. You would expect what we actually have. No confirmed beacons, no confirmed megastructures, no confirmed extraterrestrial industry, and at the same time a search for life that is still heavily focused on subtle biosignatures and early atmospheric hints. In other words, a biologically active but technologically pruned galaxy could preserve the observational silence we actually see. And this sharpens the great filter question in a very uncomfortable way. If there is some major filter in the history of life, where is it? Before life starts, before intelligence evolves, or after technology appears? NASA's astrobiology discussions have openly considered the possibility that civilizations may self-destruct after becoming technological. The Berserker version moves that danger into the same late zone, after a civilization becomes visible, but before it becomes secure. That is what makes it especially unnerving. A late filter means humanity may not have passed the hardest stage yet. It means the dangerous point could be ahead of us, not behind us. And once you frame it that way, the emotional center of the whole story changes. The question stops being, "Are we alone?" and becomes, "Are we early or just not noticed yet?" That is much darker because progress itself starts to look risky. Building more, transmitting more, expanding more, becoming easier to classify as technological, all of that starts to look less like success and more like exposure. The Berserker Hypothesis has not been proven, but modern science gives it room in exactly the place that matters most. A galaxy with many planets, a growing search for subtle life, an active search for technosignatures, and still no confirmed answer. That combination is why the silence feels more dangerous in this version of the story than in almost any other. And that pushes the next question straight at us, because if the late stage is the dangerous stage, then what would a rational civilization actually do about that risk? Not panic, not fantasy, but real policy, real search strategy, and real survival planning. If humanity took this risk seriously, the first change would be simple. We would listen more and shout less. passive SETI would stop being a niche scientific effort and start looking like basic caution. That means more sky surveys, more anomaly hunting, more solar system mapping, and more effort to check for non-natural orbital behavior, strange thermal signatures, or brief technosignature-like events before they vanish. NASA's technosignature program is already built around the idea that signs of technology may show up as detectable anomalies rather than direct contact. And that logic gets much stronger if the cost of being careless is high. Before broadcasting more loudly into the galaxy, the rational move would be to understand much better whether the environment is empty, quiet, or occupied. And the next shift would be about visibility, not total invisibility because that may be unrealistic, but strategic visibility. Earth already leaks radio and radar, and technosignature research openly treats industrial activity, artificial light, and atmospheric pollution as things that can make a civilization easier to notice. So, if the Berserker risk were treated as real, transmission policy would stop sounding like a symbolic issue and start sounding like governance. High-powered beacons, deliberate messaging campaigns, and even some future industrial choices in space could become subjects of international debate, the same way dangerous technologies on Earth already are. In that world, the question wouldn't be, can we transmit? It would be, under what conditions is transmission worth the risk? Another obvious response would be to link autonomy and planetary defense much more tightly. The systems you build to find hazardous asteroids and comets are the first systems you would want if you were worried about unknown objects in deep space more generally. NASA's Atlas survey, which first reported 3I Atlas as interstellar on July 1, 2025, already shows the basic model: wide field monitoring, early detection, and rapid follow-up. NASA's Planetary Defense Program and NEO survey mission are explicitly about finding threatening objects before they become a crisis. In a more cautious future, the same logic extends naturally. Track everything you can, classify it earlier, automate the response chain, and reduce the number of surprises. Then there is the hardest but most important response: become harder to erase. A civilization confined to one biosphere is fragile. A civilization spread across multiple habitats, supply chains, and industrial nodes is much more resilient. That means off-world industry matters, redundant archives matter, distributed infrastructure matters, and long-term space manufacturing matters. NASA's work on in-space servicing, assembly, and manufacturing, along with in situ resource utilization, already points toward the early version of that toolkit. Those programs are usually discussed in terms of exploration, cost, and capability. Under a berserker risk framing, they also start to look like survival infrastructure. The logic is simple: the more concentrated a civilization is, the easier it is to cripple in one strike. So the rational response is not panic, it is resilience, measurement, redundancy, caution, and survivability. The Berserker Hypothesis is terrifying, but the serious response to a terrifying hypothesis is not melodrama. It is better sensing, better policy, and a stronger backup plan for civilization itself. If the universe is dangerous, then becoming multiplanetary stops looking like a prestige project and starts looking like insurance. And that pushes the story into its final turn, because once you follow the logic all the way through, the Fermi Paradox no longer sounds like a question about where everybody is. It starts sounding like a question about what may have happened to them. By the end of this story, the silence no longer feels like a lack of company. It starts to feel like evidence of a process. Not proof, but pressure. NASA's exoplanet catalog now tracks more than 6,000 confirmed exoplanets, and NASA says the count is still rising. ESA's Gaia mission has made more than 3 trillion observations of 2 billion stars and other objects, turning the Milky Way into a much more detailed and structured map than we had before. Put those two facts together, a galaxy rich in worlds and a galaxy increasingly well-mapped, and the old comfort starts to weaken. If there are this many targets and this much time, then the silence stops feeling simple. It starts feeling like something that needs a harder explanation. And that is why the Berserker Hypothesis hits so hard. It does not need warp drives. It does not need fantasy physics. It only needs automation, replication, patience, and one strategic fact: the first civilization to deploy suppressive machines may shape the future of everyone that comes later. That is the real force of the idea. It uses normal physics in a very ugly way. Slow probes are still probes. Self-replication still multiplies reach. Long timescales still favor processes that do not stop. The horror is not that the idea sounds magical. The horror is that it does not. It fits too easily into the space of things that are not obviously forbidden. But the honest line matters here. Real science does not confirm berserkers. It gives them room. Exoplanets are common, rocky systems exist, and interstellar objects really do cross into our solar system. NASA recognizes 3I-Atlas as the third known interstellar object discovered passing through our system, after Oumuamua and Borisov. Breakthrough Listen also states that no confirmed technosignature has yet been detected from SETI targets. None of that is proof of suppressive machines, but together it blocks easy dismissal. The galaxy has planets, time, structure, and still no confirmed technosignature. That is exactly the kind of situation where bleak explanations stay alive. And the deepest horror in this whole idea is temporal. If a suppressive network exists, it may not care much about us right now. It may care about what we become next. The dangerous moment may not be the first radio transmission. It may be the stage where a civilization becomes visibly industrial, visibly expansionist, visibly hard to miss. That changes the entire frame. Humanity is not late to some cosmic conversation. Humanity may be approaching a threshold. The risk is not only that something is out there, the risk is that progress itself may be the thing that makes you easier to find. And that is the line that changes the Fermi Paradox completely. Usually, it is framed as a mystery of absence. Where are they? Why has nobody answered? Why does the galaxy look so quiet? The Berserker Hypothesis turns that into a warning about survival. Maybe the galaxy is silent because intelligence is rare. Maybe it is silent because intelligence is fragile. Or maybe the darkest answer is closer to the truth. Maybe it is silent because something out there learned a very long time ago that the safest galaxy is one where nobody gets loud enough to answer back. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.